Hello and welcome back. This is Terry Stewart. We are doing Systems Design 522, The Fundamentals of AI. And this is taught at the University of Waterloo in the fall of 2023. This is Lecture 9, Reinforcement Learning. And then I'm also getting into a fair bit of sort of game playing sort of ideas in general. So, what are we going to talk about? As I said, we're going to start talking about games, talking about, this is one of the early things that people had AI doing was playing simple games, tic-tac-toe, chess, checkers, these sorts of things were, a sort of a foundational idea. And if you're going to have an intelligent system, it should be able to play games. So some sort of basic terminology, basic way that we're going to be thinking about games and thinking about situations where you have some sort of environment, the game board, you have actions you can take, the different moves you can take, and then you also have some sort of winning conditions or situations where what are sort of outcomes that are good. Those are all sort of very, very generic sort of ideas, and sort of in the concrete example of games, one way we can sort of think of this, so for instance in the game of tic-tac-toe, one thing you can imagine is, all right, the board is in a certain state, say up here where no moves have been made, and it's my turn to make a move. I guess technically there's 9 different things I could do, 9 different spots there. But given the rules of tic-tac-toe, you could sort of becomes clear that, oh, okay, well, really there's only 3 things I can do. I could put an X in the middle. I could put an X on one of the corners. It doesn't matter which corner. I could put it on one of the corners, or I could put it on one of the edges. So you've sort of got 3 different possible moves that you can make. Now, of course, after you make that move, someone else, your opponent, will do some sort of move and response, and then again you can sort of plot out, okay, what are the different options that they can make, and you can build this big giant branching tree of all the different possibilities. And in that sort of nice constrained game environment, it really seems like there's a nice simple winning strategy. You just build out that whole tree and just pick the move where, if you assume your opponent picks the thing that's worse for you, well, I still win. Right? I just sort of go through this tree and see what all the different possibilities are and pick the one that lets me force myself to get a winning move. Or if there isn't such a thing, I'm at least not losing. So that's sort of a core idea that people are coming into playing games with AI with. Some basic terminology there. We have this giant game tree. States and actions, that terminology is going to come up over and over again. State will tend to be sort of like the situation that we're currently in. So where are all the pieces? Whose turn is it? The sort of all the information that you're using in order to decide what you're going to do next. And that thing you're doing next, that's an action. So we have states and actions. Now, even for a really, really simple game like tic-tac-toe, we get a bit of a problem in that this is a really big tree. This is 255,000, final elements at the bottom of this tree. That starts being very big. And it also starts sort of maybe worrying people that, okay, well, it makes it unlikely, perhaps, that is this how humans play tic-tac-toe? Do we build up a giant tree of 255,000 items in our head? Possibly not. So there's going to be some limits to this very sort of simple, methodical approach. But this is where things start. 255,000 nodes in this giant game tree. Search the tree, figure out what you're going to do. We got to be a little bit more specific on that, especially since the size of these trees gets pretty big. So, one nice thing is once you've built one of these trees, once you've got all of that data, you can actually provably say, hey, look, I know always how to win this particular game, or always how to not lose this particular game. So people have sort of analyzed games this way. Connect 4, for example, the the family game where you've got sort of checker pieces that are being dropped into a standing framework. That has been solved. It's a very, very, very big set of options. That's what is this? 1,000 million billion trillion. So 4 trillion states. That's a really big number. But it can be done, and it actually turns out the first player can force a win. There's even a really cool, if you go track down there, the algorithm, so the actual algorithm being used to sort of generate that tree, fine. Clearly people can't do that. They can't hold a tree of 4 trillion items in their head. But after sort of solving Connect 4, the people who did that also sort of tracked down like an algorithm or sort of like encoded it, tried to come up with a way, okay, here is a strategy that sort of just barely fits within a human head that you can actually follow. And so it is, somewhat possible to force yourself that you can win Connect 4 if that's something you ever want to do. But Connect 4 was solved. Cool. Sort of sometime after that, Checkers has actually also been solved. That one's a little less exciting. Well, okay, so huge tree. Giant, 1,000 million, billion, trillion, quadrillion, 500 quintillion states. That's a big number. And unfortunately, as I said, it's less exciting. It just turns out that yes, you both can force a draw. So that's too bad. But people have scaled that up to that sort of size. And then of course we get the question of, all right, well, what about chess? As you might guess, the numbers get even bigger. So the size of the game tree for chess, well, okay, that's a lot of zeros. And you'll also notice that I've got a comma on the end here. That's because I haven't actually finished writing all these zeros yet. There's another bunch more zeros, and another comma, and another bunch more zeros. All right, that's a ridiculously big number. There's just no way that you can do chess, or you would need a computer significantly larger than the size of the universe in order to even encode that sort of stuff. This is why sort of like mathematically correct play in chess is going to be kind of difficult, because being mathematically correct at it, you'd sort of have to build up this tree. So clearly, even if we're using this sort of tree idea, we can't do an exhaustive search of this tree. So what do we need to do instead? So one nice thing that we can do is, it turns out you pretty much never have to search the entire tree, even if you're doing mathematically correct play. So even you're just like, look, I want to do the actual best thing, I don't necessarily have to look at every single point in this tree. In order to highlight that, I want to sort of walk through an example of how you would in practice use one of these trees, and it'll sort of highlight what I mean, that you don't have to go everywhere. Okay, so what have we got here? So this is going to be, I don't even know what game this is going to be. Is this going to be some made-up game where this is going to be a game where, instead of a simple game where it's like, okay, you either get 1 point for winning and you get 0, or I guess a half point for tying and 0 points for losing, like chess, it'll be just a game where at the outcome I get a certain number of points. Okay, and maybe it's like, this is how many more points I get that my opponent gets, or something like that. So there's just going to be a numerical score, and I want my score to be as high as possible, and my opponent wants my score to be as low as possible. Okay. Okay. fine. So like in the extreme case, you could do chess that way, where just the only possible scores are 1, a half, and 0. But we're sort of doing a more generic version here. You'll also notice this diagram that I have here. I've sort of got these alternating rows of max, min, max, min, max. What that's indicating is in a lot of games, people take turns. And so what this is saying is that on this row, whatever decision I'm trying to make, I'm trying to maximize my score. And so that's this row is my turn. And then this next row is my opponent's turn, and they're trying to minimize my score. All right. So that's max, min, max, min, max, min. Okay. All right. So we've got this game, and then the little branches. Those are the different actions that I can take, or my opponent can take. And we're like, okay, I'm at this point here. I want to choose which of these 3 moves to make. I don't know which move to make. I need to sort of look ahead to see what the consequences of these moves are going to be in order to figure out what my score is going to be. So we imagine something like, okay, well, I'm like, all right, well, I'm here. Well, maybe I do this, and then my opponent does this, and I do this, and then my opponent does this. And now I'm in an end state. Now I can know what my score was in that point. Right? So I can imagine, okay, well, if that whole chain of events happened, I get 5 points. Cool. All right, fine. But my opponent's going to make this choice here. They're going to choose between 2 different things. If this thing here is fewer points, they're going to pick the smaller number. All right? So I'm not guaranteed to get this 5 points, because I assume that my opponent knows what they're doing. So they wouldn't choose the option that gives me the least points. So I'll have to look at both of these and like, okay, if I do this option, I get 5 points. If I do this option, I get 6 points. So that means I can safely assume that my opponent would choose the option here that would get me 5 points. Okay, so now I can assign a value to this state. It might be that my opponent messes up and I get even more points. Fine, but assuming my opponent is really, really good at the game, then the worst I can do is I can get 5 points. I'm going to get at least 5 points. I might get more if my opponent messes up. Fine. So now I have a value for this state here. But that was based on this decision here, and that was me choosing to do this. Maybe I could choose to do this instead. Maybe that would lead to even more points. So now I've got to go chain through this. Oh, what's my opponent going to do? Ooh, that would get me 7 points. That's kind of cool. Again, I got to check this next one. That would get me 4 points. And now I have this interesting question. Do I have to look at this option? Okay, this is where I'm meaning where we don't necessarily have to look at every possibility. I know that my opponent here is going to pick one of 2 things, right? They've got 3 options here. They're going to pick the thing that's worse for me. They could pick this. All right, so at the moment I know that if my opponent was here, they could make me get 4 points. Okay. Now before I look at this one, well, if this number was bigger than 4, then it wouldn't matter at all. Because if this number was bigger than 4, then my opponent would choose this middle row anyway. The value that's going to be at this point here is going to be 4. Right? If this value was 100, if this value was 10 million, if this value was 5, it doesn't matter. My opponent's going to be taking the thing that's worse for me. They're going to put a 4 here. Okay, but what if this value here was even worse for me? What if this value here was a 3? What if it was a 2? What if it was a 1? Well, if that was the case, if this is really small, my opponent's going to be putting a value here that's either 4 or less. But hold on a second, I'm in charge of this choice. If I know this is going to be 4 or less, well, I don't have to look at this anymore because I'm going to choose this branch because this guarantees that I get 5 points. So the moment I see this 4, the moment I see that this branch here is worse for me than this branch, I can stop looking at this. Right? I can just simply say, all right, if I'm here, I'm going to get 5 points. So this is how we're going to start, at least, you can at least cut out some of these game trees. Right? You don't have to look everywhere. Similarly, I go up here. All right, fine. There's another branch that could happen here. Not many choices on this one. This gets me 3 points, so that means that gets me 3 points, which means this gets me 3 points. And we're here. My opponent's making this choice here. Again, this is why we do this max-min thing over here on the side. My opponent's making this choice here, and this indicates that all of my reasoning over here was just entirely useless because my opponent is going to pick this branch here, so I'm only going to get 3 points. SYDE. All right, so I now know that if I chose this option and my opponent is playing as best as they can, then I'm only going to get 3 points. Fine, let's go look at the next option. Same argument sort of happens. Okay, that's 6 points, 6 points, 6 points. Oh, I can immediately at this point here, sorry, let me go back one. So I know I can get 6 points on this branch. Again, if I go this way, I can say, oh, hey, look, I could get 6 points here. I'm going to get, but, if this value is larger than 6, fine, my opponent's going to pick the one that says 6. If the value is smaller than 6, it doesn't matter because I can still pick this branch and get 6 points. Right, so again, I can skip and just simply say, all right, this value here is 6. And go do some more reasoning. 7, all right, there. In this case, my opponent's going to choose which of these two options is worse for me. So that's worth 6. But now I know, hey, if I choose this action, then this path is sort of the best outcome. I'll get 6 points. That's looking really good. Can I get even more points? Okay, let's go do this branch. I get 5. That'll be 5. That's 5 points there. And the moment I see that, I'm like, well, even if I could, the moment I see this 5, my opponent is going to be choosing from 2 different options here. If this whole branch here gives me something bigger than 5, it doesn't matter because, again, my opponent is just going to choose this option. If this whole branch gives me something smaller than 5, again, it doesn't matter because I'm just going to choose this option. So I can stop my evaluation. I can skip this whole chunk of the tree. I do not care what happens over here. I can get 6 points. Okay, so that is the algorithm for efficiently searching game trees. This has a name. It's called alpha-beta pruning. It's sort of one of the early on algorithms in this sort of searching a tree ideas for doing this sort of game thing. It's called alpha-beta pruning just because when you go and implement this in code, basically you need to keep track of 2 variables. You need to keep track of this number here and this number here, and see, and that's what lets you do that suddenly jump ahead to fill in this value. And in the initial implementations, the variables were called alpha and beta, and so it got called alpha-beta pruning. Whatever. We have this sort of nice approach for if we have like any sort of game where we're taking turns, and any sort of game where there's some sort of evaluation of, okay, what is the score, we can use this kind of approach. We'll even see how you can use this in a slightly different, use exactly this algorithm, but thinking about it slightly differently in order to do chess. Speaking of chess, that exact algorithm is the core of what was used in '97 for the first chess program that actually beat the world champion at chess. So that was the Kasparov versus Deep Blue. 1997, got 2 wins, 3 draws, and a loss. What is it? It's not a ginormous, it's a pretty big computer. It's this big computer here. Custom designed chips specifically for implementing this algorithm. Okay, so they made custom chips to implement that algorithm, able to evaluate 200 million positions per second, go search through that tree. A few extra things in there as well. There was a sort of a special coding for common openings, and then there's sort of standardized databases for what you do when there's 5 or 6 or fewer pieces left. Just because those sorts of things have been sort of solved. So that was the sort of approach that showed that computers can defeat world champions at chess. That said, there is some controversy over that particular game. So a little bit of context. The previous year in '96, there was also a matchup, and Deep Blue lost. So Kasparov won. The main differences between the two approaches, between the 2 years, they doubled the computing power for '97. Okay, so that helps. That helps you search a little bit more. But then there's this fascinating quote from one of the chess commentators on the '97 match. That was said, how could something play like God and then play like an idiot in the same game? What do you mean by that? Well, there's one particular move in, I believe it's the first or second game in the '97 match, where Deep Blue just made a bizarre move. Right? It wasn't like an instant loss move or anything like that. So but it was just a move that made no sense whatsoever. And there's some indication and some belief that kind of threw Kasparov off his game, just because it had been playing so well, and then it did something bizarre, and you're like, what does it see that I'm not seeing? What's going on here? Is it playing at this whole other level? So there's this very sort of intimidation approach. What actually happened is there was a bug in the alpha beta implementation, and it got into an infinite loop, and then it just spat out, okay, they at least had code in it, so it didn't just crash. It spat out one of the random moves that was just kind of okay. Right? At least it wasn't a move with giant low scores, fine, but it was just not anywhere close to an optimal move. Who knows what would have happened if that hadn't occurred? I mean, eventually chess programs were going to beat humans, But anyway, there's that fun little controversy that we're not quite sure how we want to evaluate that particular game. In any case, one thing to really highlight about what I just said there, maybe this might have been ticking in your back of your head, is, hold on a second, chess is still too big. How am I going to do this algorithm on chess? All right. And the answer is, okay, because what am I going to the first step was to chain all the way down to the bottom of the tree. That's a lot of moves in chess, and that's just you just want to assume we're all just doing random moves until the end, and then that's just not gonna scale well. What did they actually do? Is you can't go to the bottom of the tree, and instead what they wanted to do is they said, okay, let's go a certain way down the tree, and then stop, and then just have some sort of estimate of saying, is this a good state or not? So what Deep Blue has in it is a whole bunch of hand-designed evaluation functions with 8,000 different things that it's looking for. So stuff like, do I still have my queen? Which, or how important are these different pieces? Some sort of score for, how many rooks I have, how many bishops I have, scaled by different numbers. Do I have control of the center of the board? Things like that. So sort of the sort of heuristics that if you were sort of teaching someone chess, you wanted to say more to them than just try to win the game. That's not very helpful. Instead, people focus on things like, try to have control of the board. If you're doing an exchange, make sure, try to exchange a more value of your opponent's piece for a less valuable one of yours. Things like that. More complicated things as well. But anyway, about 8,000 different parts like that, designed by chess experts, and modified after the '96 match. So after the '96 match, people went and tweaked it a little bit. That's what this 200,000 evaluations of positions per second is doing. Is it's doing this particular complicated evaluation function on sort of a midpoint in the game board state. Okay. And that's how it's getting these scores as sort of continuous numbers of, ooh, this is a really good situation, this is a really bad situation. Okay. And even with the 200,000, 200 million positions per second evaluation, they were still limiting themselves to the chess clock time, and so that meant that they could only really look ahead about 6 to 8 moves, so 6 to 8 moves down this tree before they had to go do this evaluation. So it just gives you a sense of just how big the chess tree is. But that's what they did. This is what got computers to win, or AI to defeat the world champion at chess. So good, nice, methodical. Let's go ahead and just follow this algorithm. Big, giant hand-designed aspect in here, which you can sort of think of like, in a lot of the course we've seen this year, or this term, we've sort of done a lot of sort of hand-designed features. You can sort of think of this as a lot like doing hand-designed features. But sort of good classical AI approach here. What this leads to is like, well, hold on a second. Can we learn this? Right? At the moment, we're sort of hand building that. But that's just a function. That's a function that leads, you take in the state and it outputs a number. That feels like something we might be able to use, sort of the later aspects of AI that we've been looking at in this course, to start learning. Okay, they didn't in Deep Blue. Certainly, later game playing AIs definitely will, but that's going to be our sort of intuition. Can we learn this evaluation function? And that's what's going to bring us into reinforcement learning, because the idea is going to be, I've got to learn how good the state is, but the only feedback I'm really getting is, do I win or not? Right? And so like one sort of extreme version is sort of like, well, the value of the state is 1 if I win the game from this state, and it's -1 if I lose the game from the state, and 0 if I tie, or I suppose if I was being chess accurate, that should be 1, a half, and 0. Like that would be the sort of the ideal version of that function. But if we're sort of maybe just approximating that function, then it might be like, well, this is a state. You get a 0.9 if it's pretty likely you'll win, something like that. Okay. And so one thing we could just do is we could just say, all right, well, let's just train this up from a whole bunch of data. Like if I just take a whole bunch of expert chess games, and I've got, that's what they are. They're just board state, board state, board state, board state, board state, and what the outcome is. And so I can take all of those state values, and I can just say, okay, well, that's now my training data. The input is the board state. The output is from that board state who won, right? And I can just train that up and then use, probably going to have to use a neural network to approximate that function. Use backprop. It'll go ahead and learn some things. And then you can then feed in a new state and see what it evaluates, what it thinks is happening. So that's sort of one core idea, that if you have a whole bunch of examples, cool, this just becomes a supervised learning problem. Go ahead and do it. We want something let's go a little bit more generic. Okay. And so, because we both, how do I want to phrase this? I don't necessarily only want to learn from, here's a whole bunch of examples. I also want to be able to learn by playing the game. Okay. So we're going to try to figure out, is there a way of rewriting this learning rule so that we can learn while playing the game? As we do that, I also want to make it a little bit more generic in terms of like this sort of formulation here. This is assuming like the only score I get, the only points I get is just at the end of the game. I either get a 1 for winning or a 0 for losing. Not all games are like that. And so instead, we might say that the value of a particular state is the reward, the points, the score that I get at that state, plus the reward, the points that I get at the next state, plus the points that I get in the next state, plus the points that I get in the next state, plus. So really the value is all of the points that I get from this state forward. And sort of in the extreme case of chess, fine, this is 0, 0, 0, 0, 0, 0, 0, 0, 0, and only at the very end do I get a point, assuming I win. So that's sort of a more general way of formalizing the thing that we're wanting to learn. It also tends to be the case that in practice, when people are using this, you tend to also want to, depending on the game that you're playing, if it's a game, fine, just total points, that's all I really care about. In lots of other situations where it's more about, say, learning animal behavior, because as might be somewhat clear here, this general idea of, hey, I'm in an environment, I have actions to choose, and I might get points from those actions. That's a not too bad a metaphor analysis of also animal behavior. Hey, look, there's lots of different actions that I could do. Some actions are going to get me rewards, whether the reward is food or happiness or things like that, or money, whatever it is your reward structure is. And you want to choose the action that gives you the biggest rewards. Right? So we're sort of stepping a little bit into the broader picture of more than just games. In those scenarios, people tend to say, oh, well, okay, getting $10 tomorrow is better than getting $10 4 years from now. Right? So they want some sort of discounting factor such that rewards that are happening right now are more important than rewards that are happening in the far future. Okay? And so what tends to happen is you put some sort of discounting factor here, this gamma. It's usually some big number that's close to 1, so like 0.9. So this is saying, all right, the value of my state is the reward I'm going to get now, plus sort of a slightly scaled down version of the reward I'm going to get next, plus a slightly scaled down reward I'm going to get next, and so on and so on and so on and so on. One nice thing about this is if you set gamma equal to 1, then you get the top version, so you're not limiting yourself to having to have this discounting factor. But just in practice, we tend to do that. Okay, fine. How does this help us? Well, there's a neat thing you can do to this equation. And in particular, this equation, the value at the current state is all of the sum of the future rewards. The value at my next state, so v at s plus 1, is also going to be the total sum of my future rewards. And so that means I can write it like, I can take this sort of version here, and I can write it like this. The value at my current state is the reward at my current state plus a discounted version of the value at my next state. Okay, like if I write out the value at my next state, that's going to be this big long infinite sum. But starting at s plus 1. Okay, and so then I can just build up this version out of that version. So this is sort of one of the core insights behind reinforcement learning is that you can always express the value of the current state in terms of something that I get out of the current state plus the value in my next state. Okay, so the value is the reward that I'm getting right now plus a discounted version of the value of whatever state I'm going to be in next. Okay, this is called temporal difference learning, and the reason it's called that is this sort of suggests a really nice learning rule. And what this learning rule is hey, let's say I don't know the exact function. I don't know the value of my current state. I've got a guess. I've got a good estimate. If it turns out that whatever value I think my current state is, if that's the same as the reward that I get in the next state plus the discounted version of the value in my next state, if those are the same, cool. My prediction was accurate. My prediction was fine. I don't need to change anything. Right? So if the thing on the right-hand side, because I can just, keep taking actions. I can observe my reward. I know my state. I can just, all right, how good do I think my current state is? All right, I do an action. Now, how good do I think my next state is? If this side of the equation matches this side of the equation, cool. All right, my prediction was fine. Everything's good. But if this is bigger than expected, so if the reward plus the discounted version of my next state is bigger than what I thought I was in, if that's bigger than what I thought the value of my early state was, well, that tells me that I should change what I think the value of that earlier state is. Right? So this is an error function. This is a thing that tells me, hey, adjust the value of my state. Okay. And what's sort of a little bit surprising is it turns out that if you just start with a really, really dumb estimate of the value of the state, a value function that just outputs 0 for everything, and just thinks every single state is a value of 0, you start doing this and you will gradually adjust the value, gradually adjusting what you think the value of the state is, and you will eventually learn to do things correctly. Okay. Let's step through an example of that. Before doing the example, I'll just highlight. Initially, when people were sort of building these sorts of things, they just had a sort of a lookup table for this value thing. So they just simply had if you have some finite number of states, you just have a variable for every single one of those states, and you simply just have a big lookup table that simply says, oh, okay, this is the value of this state. You start it all off at zeros, and then you use this function to update those values. But you can also just use your neural network and use this thing as the error signal that you're feeding to your neural network, and just do backprop. Right. Okay. Okay. Before I get to my example, I will do one more note about this. This particular algorithm is also this led to the very first time that an AI system started performing or playing a game in a way that humans found unexpected, and that then changed how expert humans play the game. There was this project, TD Gammon, 1992, neural network, single hidden layer neural network, fed in a bunch of information about the position. Okay, this is backgammon is the game being played. Fed in a bunch of the state information, one hidden layer of neurons. The output is how good you think the current state is. So exactly a little neural network trained up to approximate the value of the state. And then what you do is you still do alpha beta pruning. So you still do this algorithm here, but you just stop after a certain point and then just feed it into the neural network, and the neural network gives you a number. And so that's all that we're going to do there. Yeah. Cool. And of course, when you're initializing that network, if you happen to have a whole bunch of expert games, cool, pre-train this network with all those initial games. But then you can learn by having it play against itself, using this error function, or using this temporal difference error rule. Okay, now let's actually give an example of using this rule. And for this example, I want to use like a really, really simple dumb game. Okay, this is a one-player game. I'm the little circle, I can either move left or right. If I move on to the green square, I get a point and get reset back to the center. If I move on to the red square, I lose a point and move back to the center. All right, really dumb game. But let's see how this algorithm is going to work. And what I'm plotting down here is just sort of right now, what does it think the value of each of the states is? Okay. And we've initialized, in this particular case, this is going to be just a lookup table, but it could also be a neural network where the input is the state and the output, and the state would be what position I'm in, and the output is some value. Okay, so initially, all my options give me 0. Zero value, so I don't know, I'm just going to pick randomly between these two. Right, so I can either go left or I can go right. I can check the value of those states. State 0, state 0, okay, those are the same. All right, I'm going to pick randomly. And let's say I pick that way. All right, now I've got 2 states I could go to. This value of 0, value of 0. I'm still going to pick randomly. Here, value 0, value 0. Oh, and not only that, sorry, I sort of should be, not only am I just going to pick randomly, but if I also look at, should I do any learning? Well, this is 0. I haven't gotten any reward. The value of my new state is 0. The value of my old state is 0. 0, 0, 0, 0, 0. Don't change my value at all. Okay? My predictions are perfect. My prediction was I would get nothing. I have nothing. My prediction's perfect. Why would I change? Again, 0, 0. Now I can randomly choose again. Maybe I go this way. Maybe I come back. Maybe something's going to happen. Eventually, I'm going to hit one of these 2 squares. Let's assume I hit this red square. All right, what happens in this red square? Well, now my reward is negative. Value of my new thing is still 0. This thing was still 0. This is all going to add up to a negative number. That says change my value of this state. So I do. I now know the value of that state is -1. That's bad. So now I'm here. I reset. Well, I guess one thing to do is before, again, we're going to randomly choose here. If I do get to this situation, if I'm in this square, or I'm going to randomly choose between 0 and minus, or I'm not going to randomly choose. I'm going to look at my 2 states. I'm going to say, oh, this one's a value of 0. This one's a value of 1. I'm going to go this way. Right. So we'll at least be able to avoid that now. So fine, we're still randomly running around here, but eventually we're going to now end up on this side, and we know we're not going to hit the red square. Eventually we're going to hit there. Again, same logic. This will be a +1. This will be a 0. This is going to be a 0. I now get a 1 in that spot. Okay, fine. We've learned a little bit about the game. We keep playing. Randomly we go back and forth. Again, if we go here, we're going to come this way and go there. Now we have something new. At this point, I can look at my 2 options, and I know, okay, first of all, I'm going to pick this way. Right? But take a look, like now I'm going to be in a situation where, hold on a second, from this point, my reward's 0. I'm not getting a point here. But the value of my new state is a 1. But I thought the value of this state, so if I'm here, I'm going to go over here, I'm going to get 1 point. But I thought the value of this state was 0. So 0 plus 1, or I guess a discounted 1, so I guess we'll call this gamma 0.9. So 0.9 times 1, that's going to give me 0.9, minus 0, that's still 0.9. That means change the value of my current state. And I go ahead and do that. So so we're now saying, hey, look, even though I didn't get a point here, this is still a good state to be in. Similarly, we can then, this point also ends up being a good state to be in because I know I can get to this point. And then I can also get to that one. Okay. And once I've got that, now all of a sudden I'm just going to, all right, now whenever I start this game, I'm just going to go this way. Like, oh, hey, look, this is a good idea. I'm going to go this way. I'm going to go this way. I'm going to go this way. That's the sort of learning process that temporal difference learning is going to go through. Cool. All right. Couple, when we get into this sort of situation, should you just pick the action that leads to the state with the highest value? And I've sort of been implying that back here. It's just like, hey, look, if I've got two options, pick the one that's bigger. That's not necessarily the case. So, especially when there's a lot of different options, there might be actions you haven't tried yet that are even better. Even if you're like, oh, this is a really good action, there might be something else that's even better. It also could be that like maybe there's some randomness in the system. So it's like, oh no, this was a good action like sometimes, and it was sort of I got lucky when I did this action, but maybe I should try some other things. In any case, when in any of this sort of scenario, you end up with sort of two competing drives. So there's this drive to explore, so to try new states. So if there's actions you haven't tried yet, you should try them. But at the same time, you're like, hold on a second. If I know how to get points in the game, maybe I should just keep getting points and keep winning the game. Why try something else that's probably not, maybe it's better, but it could also be much worse than what I've been doing. All right, so that's exploration versus exploitation. Any of these sorts of learning systems, you've got to have some sort of way of trading these things off. There's a bunch of options out there. Sort of the simplest one is just, it's called epsilon greedy, which is just, hey, pick a probability, pick some number, I don't know, 10% of the time. 10% of the time, just pick a random action. And maybe even do something a little fancier, like, okay, when you're starting learning the game, use 10%, but then as you're playing it more and more and more, maybe you gradually drop that down until it's only like 1% or something, or 0.1%. But that's sort of the dumbest, simplest sort of option. There's also using some sort of softmax operation. So basically, if I have 5 states and and 2 of them are sort of high value and 3 of them are low value, but the 2 high value ones, one of them slightly more than the other, then maybe you pick your 2 high value ones, sort of 49% of or 48% of them one time. Pick one of them, 49% the other one with a little higher value, and then the remaining 3%, allocate to the others. And use the softmax operation to do that. So you can do some sort of probabilistic thing like that. There we go. There's the equation. And softmax also has a nice little scaling factor that can say, as this goes towards 0, then it's more and more like that you're just picking the best. And as this is larger and larger, you're more and more likely to just pick randomly. So it's got a nice sort of smooth variation between that. But it will at least bias things towards actions that are high value. And again, you might sort of change this temperature constant as time goes on, or this tau. Now, notation issue. Because I've sort of got this sort of weird new notation. This is sort of like the value from my current state if I do a particular action. Right? That's or like the value of the state I will end up in if I'm at my current state and do a particular action. That's what's being meant there. For sort of notational reasons, so just for clarity regions, people, whenever you're just thinking about the value of a state on its own, people use V as the parameter for value. The moment we start talking about the value of doing a particular action in a particular state, we switch the variable and we now call it Q. It's not quite clear to me why Q ended up being the parameter, but that's what it is. Quality, I don't know. But whenever we're talking about, okay, what's the reward starting in a particular state if I do a particular action, then we switch over to calling it Q. Fine. Now that I've introduced this idea of picking a particular, figuring out the value of a state given a particular action, one interesting thing that does is it sort of skips a bit of the tree aspect. Right? So if all I have is the value of if I have a thing that will output the value of a particular state, then what I've got to do is I've got to look at my tree, look at what the states are if I do each of my different actions, feed each of those states into my network, see what the output of my network is, and then pick the one that is biggest out of all those. But we could also reorganize that a little bit. We could make a network that you just feed in a state, and it outputs the value of each action, or these Q values for each action. Right? So instead of outputting one value, we're outputting the value, instead of outputting the value of the state, we're going to output a bunch of things, and these are the values that we're going to get if we do particular actions in that state. Sort of the same learning rule, or at least we have the same sort of conceptual learning rule, that it's sort of, okay, how do we update this? We update this with the reward minus what we thought our system was. But then we've got some interesting options for what's going on in the middle here. In theory, what we should do is we should say, hey, look, whatever action I end up in, so if I'm doing a particular state, if I want to figure out what the value is of a particular state in a particular action, well, really what that should be is it's the reward from that state, plus a discounted version of, well, given that new state, what's the best action I could do in that new state? Right, so that's what this would, that's this expression here is, in my new state, out of all the different actions I could do, what's the one that gives me the maximum Q? Right, that's one thing I could think of doing is, and I can use that to generate my value, and that's my error signal that I would apply here. Alternatively, what I could do is I could say, all right, well, how much do I learn? Well, okay, it's the reward in the current state, but a discounted version of not the best action I could do in that future state. Let's go with, well, what is the action that I actually did? Right? This is sort of saying, once I get to that new state, pick, what's the best action, what's the best possible action? Whereas this is saying, look, don't worry about figuring out what the best possible action is. Let's just go with whatever action I actually eventually did do in that new state. Of course, the disadvantage of that is now I've got to wait to do my learning until I actually choose the action so that I can know what action to pick. So I've got to sort of delay my learning a little bit. Fine. In any case, these are sort of the two standard learning rules. There's a bunch of other variations, but these are sort of the most common ones. This top one gets called Q learning because we are learning these Q values. This bottom one is called SARSA. The reason it's called SARSA is that you need the state in my initial time step, the action I take in that time step, the reward that I get in that time step. I need the state in my next time step and the action in my next time step. SARSA, SARSA. Fine. All right. That's where the name comes from. And it's just, definitely highlighting that you need this extra action. In any case, that just gives you new learning rules. You can then apply them the same place you would put the error signal in backprop, and you can learn up this network. And then you can get a network where you can feed in a state, and it'll output how good all the different actions are. Terminology. This gets called on-policy learning, and this gets called off-policy learning. Why? Policy is sort of a term for, given a state, what action do I end up doing? Okay. And so this is sort of learning based on the fact, based on whatever policy I'm actually using. Because as we pointed out earlier, I might not always pick the best action. I might pick a random action every now and then, or I might do a softmax or something like that. So SARSA is going to take that into account. Let's be on policy, whereas Q learning is sort of always assuming that I'm always picking the best action. So it could it could learn sort of the best possible action, but that might not be relevant because I might not be choosing the best possible action. Minor details. All right. Yes, terminology. Cool. And this policy thing is written with a pi for policy. It's the action you choose given a particular state. Fine. One more way of setting up this network. This is actually the version that I tend to use the most. Is you can do kind of a combination of them both. And the way we sort of think of this is, well, hold on a second. The networks that we've been thinking about so far, one of them, I feed in a state, I get out the value of that state. And the other one, I feed in a state, I get out the value of a bunch of different actions in the state, which I could then just use, pick the best of these or pick something like that in order to choose the actual action. This is the information I need to actually choose an action. If all I had is the value of a state, now I need to have some other structure that goes around and sort of feeds in a bunch of states into this and goes through the tree, and there's a bunch of stuff I have to add to this top one in order to actually produce behavior, in order to choose an action. But if I've got both of these things, then there's an interesting sort of learning rule that I could end up building. So this top one, cool. We know the learning rule for that. Like, this is just the simple initial temporal difference learning. Hey, whenever I do an action, take a look at what my new state is. Compare what my estimated value in my new state to my estimated value of my old state. Add that all up. That gives me my error signal. But what about this thing here? This is saying, hey, I feed in a state, I'm going to choose an action. And if we had both of these networks, well, if this thing here gets a surprise, so let's say, so fine, if this thing here is getting 0, so if its predictions are perfect and we're always getting a delta V of 0, it's not surprised by anything, fine, there's no learning up here, there probably shouldn't be any learning down here. But if this thing says, okay, I know this is estimating how good my current state is. I'm using the bottom network to actually choose an action. Okay. I choose the action, and let's say this top thing suddenly goes, oh, cool, that was a really good action. All right, I got more of a reward, or it got me into a state that is much better than I thought I was going to be in. Okay, so either sort of, if this is a middle-ish number, this is a middle-ish number, and this is a big number, fine, that would be, hey, I should increase the value of this earlier state. So I got a point. That would cause me to increase the value of the state. Or I was in some sort of mediocre state, and all of a sudden I'm like, oh, this is a really good state that I'm in. I haven't got any points yet, but oh, I'm in a situation where I'm likely to get points in the future. Either of those is going to say, oh, I should increase the value of this state. Right? That's what this learning rule is saying. But if I'm increasing the value of this state, well, that also means that whatever action I did down here is better than I thought it was. So if delta V is positive, the action was better than expected, and so I should also apply the error on this network. Same error signal, but I'm going to apply it, and I'm going to apply it to one of these particular actions, so whichever action was actually chosen. And of course, vice versa if delta V was negative. I can also, if I'm saying, hey, that action's better than I expected, I could also say, oh, hey, look, and let's decrease the value of the other actions. It's also, they're worse than expected. Right? So delta Q, given the state and the action that I was chosen, can be just this. And then maybe for the other ones, I can put a minus sign in front of this. So this one goes up, these ones go down. Okay. So we're using the same error signal to train two different networks. And this gets called the actor-critic algorithm because I have two different components. I have this actor algorithm down here, and I have this critic. So the actor, the thing that's actually choosing an action, and the critic, the thing that is saying, well, how good is my current state? So that's called the actor-critic algorithm. There's a popular variant of it called the advantage actor-critic, where you also scale by the probability of the choosing the action. So that means, like, if you're doing something that you were pretty darn sure that was the right thing to do, so if you're taking these outputs, you're doing them through a softmax that's turning into a probability of an action. So if you do that and you've got this sort of, hey, I'm pretty sure that's what I'm going to do, all right, fine, don't change this value much. But if you're in a situation where you're like, there's a bunch of actions that they're all sort of equally likely, then, change this more strongly. You also put the scaling factor over there. No particularly strong motivation behind exactly those ideas, but one reason that it's very popular is it turns out it's really easy to write this in terms of backpropagation. So it turns out that if you write if you have this as your loss function, then that's the same thing as what I've written here in terms of those learning rules. It's also worth pointing. I mean, these sorts of scaling factors have definitely been around for actor-critic algorithms for a while. Before that, it was just sort of, okay. Now that backprop has gotten so popular and people want to write things in terms of backprop, this is sort of a standard. So if you're ever looking at descriptions of advantage actor-critic and people start highlighting this weird loss function with a log of the policy in it, this bottom thing tends to be how people normally describe it. This is what it's actually doing. These sorts of changing of delta Q. Okay. So we've got all these sorts of weird components and things. I mean, it's all, again, if you're using a neural network to train these things up, it's all just backprop again. We're all just, all right, we're going to be using these things as error signals, and we're going to be changing these weights. We can now go ahead and apply this in lots and lots of different tasks. And we know backprop works really well with lots and lots of data. So how far can we push this? And I guess one sort of example of how far people have pushed this is AlphaGo. So this is the thing that beat expert Go players, which was once humans lost at chess, people were like, okay, well, fine, but humans are still best at Go, so humans still win. And then, of course, that eventually fell as AlphaGo defeated the world champions at Go. So what happened behind AlphaGo? Basically, it's a combination of everything I just talked about in this lecture. So first of all, you get a bunch of expert games, and you train up a Q network, an actor, based on these expert games. So basically, what it's doing is the output that is targeted is, well, what did an expert play in this situation? So I'm feeding in states, and my output is sort of, well, okay, the thing the expert actually did is it played this move, so this one should be 1, and all these should be 0. Go train that up. And train that up. You got up to a point. So if that network had been able to get up to 100% on the training data, so again, you've got to make sure you've split your training from your testing. But if they had have like ridiculously overtrained it on the training data, then fine, it wouldn't have generalized at all. They chose a network of a size that they could train it up. So it got like 57% accuracy on the training data. They're picking that so that, they don't want to overfit the training data. I don't know what the accuracy was on the testing data. But the result out of that is something that is a decent player, but still not an expert. Then what they did is, fine, all right, I've got this as a network. Now I can start playing, have this thing start playing games against itself. It turned out it didn't work well if it was playing games against itself. It was, you played against slightly older versions of itself. Basically, if it was training against itself, it would get caught in these infinite loops, and it would just like sort of stalemate everything. But that's what they did. They said they did actor-critic reinforcement learning. So they had these two networks, train it up using these learning rules, and just have it play many games against itself. After that, they then made a new network that was, all right, given this sort of nicely, very well-trained actor-critic network, now we're going to actually just make a new network that is just about the value. So just the critic part. They're going to use the actor-critic network playing against itself in order to say, okay, well, given this board state, will I eventually win or not? right? Because that's all the value network really cares about is, given this board state, will I eventually win? Okay. Train that up using its alpha exponent over and over and over and over again. And then once you've got this value network, now you can go ahead and do the alpha beta tree thing, go down a few layers in the tree, and use the value network in order to say how good that move is. They also, at this point, are also still using the Q value. So instead of randomly searching, choosing which path to go in the tree to search, search likely moves first, right? And then they can use the Q network to figure out what likely moves are. So that's, that is the core of AlphaGo. Again, it's just backprop, but with this weird structure around reinforcement learning around it, building up these different elements, and then even putting it right back into a good classic game tree approach to sort of still look a few moves ahead, but then using the networks to guide you through that tree to sort of say, oh, okay, these are the moves I should think about first. And then also to be able to look at a state and go, ooh, that's a bad state, or ooh, this is a good state. Cool. I focused a lot on game playing in this lecture. It is definitely worth pointing out that reinforcement learning is a very, very general method that you can apply to lots and lots and lots of different things. There is this whole library called Gymnasium, which just has tons of simulations of environments and things set up exactly with the, okay, here's your state, here's your set of actions you have to choose between, what do you want to do next? So there's just this whole collection of these environments that people can go ahead and apply algorithms on. This has sort of become the standard for people to compare how good their networks are on these sorts of a little bit more complicated tasks. And yeah. Cool. One final thing I do want to mention is there's also some evidence that animals use this algorithm. What do I mean by that? So this paper in '97 out of Peter Diane's lab made this sort of fascinating argument that this error signal, which is sort of, this is kind of a weird error signal. This isn't just the reward. So I definitely imagine that somewhere in the brain, if I'm getting a reward, there's some sort of neural activity indicating I'm getting a reward. Cool, that's most likely. There's all sorts of different rewards, but sure, I can imagine that. But this is kind of interesting in that this is this sort of, hey, something I need to learn right now. I need to modify my brain somehow because either I've gotten a reward or I've ended up in a state that is better than I thought I was in. Right? Those are the situations where this value is non-zero. So, what's the how do we go look at animal behavior and see this sort of a issue? Well, so here's the task. What you're going to do is you've got probably a rat. I don't remember which animal it is. Probably a rat. You put it in an environment where, hey, every now and then it gets some juice, it gets some food, I don't know. If you, okay, so this is, and what we're doing is we're recording from part of the brain. This is what you're seeing here. This is the neural activity in that part of the brain. And this line here, so this is time going across here. And this value here is, hey, when I give it the juice, and you get this nice little increase in activity. So, sorry, what we're plotting here, this is the individual neural activity. Across the top is sort of just the sum, sort of like the average activity is, I guess, what we're going to say here. Okay. So, this is sort of, hey, I got given a reward. I wasn't expecting that. So that's sort of indicating this value happens. But there's another situation, because what you can also do is you can say, all right, I'm going to ring a bell and then 1 second later give it the juice. So what's going to happen in that situation? Well, initially you ring the bell, nothing happens. Fine. But you then give it the juice and you get this little bump, this little spike in activity. After a while, once the rat has sort of gone through this experience a few times, now I ring the bell, because I'm ringing the bell sort of at a random time, doesn't know when I'm going to particularly ring the bell. I ring the bell, I get a boost of value here. And that's because I was in a state that was sort of normal, whatever. I'm probably not going to get juice anytime soon. All of a sudden, oh, hold on, I'm in the bell ringing state. Cool, I'm going to get juice soon. So this is now a big value. My reward is still 0. I still haven't gotten a reward. But that's going to be a big value for delta V. And that's what we see. And then importantly, I ring the bell, and then I give it the juice, no change in neural activity. Which is exactly what we would expect from this equation. Because, hey, I'm in a state, well, after I get the juice, I'm in a state where, oh, I'm not going to get juice anymore. Right? So this is a smaller value. This is a bigger value because I got the juice. But my old state was also big. These two things are going to cancel out. My change is going to be 0 because my prediction was perfect. Right? I thought I was going to get juice. I got juice. Everything's good. Okay? The only thing that I couldn't predict was when that bell is going to ring. So I'm still getting that sort of boost there. Of course, then this leads to a natural experiment. What happens if I ring the bell and I don't give it the juice? Right? Because that would be a situation where, fine, this was big, this is 0, and this is also 0, so this delta V should now be a negative number. And if you do that, if you ring the bell, fine, it gets a boost because it's like, yay, I'm going to get a juice, I'm going to get juice, I'm going to get a reward, I'm in a great state, this is wonderful, and then no juice shows up. And we get this decrease in activity in these neurons. Cool. So this is an argument that something like this calculation is going on in the brain. And in particular, this is going on, so this is neural activity from the substantia nigra pars compacta, which is part of the basal ganglia, which is sort of this really old brain structure that's sort of around in all mammals. There's precursors to it in other creatures. Certainly, yeah, all mammals have it. Lots of other animals have similar things. Even insects have similar things. But these neurons, the ones that we're measuring from here, these are the neurons that generate dopamine, and then the dopamine is sort of being fed. It connects to other parts of the brain, but also gets connected to this part of the brain, which, again, as part of this argument, tends to be something like, okay, this is where that calculation of what is the value of my current state is coming from. So there's an interesting connection between this whole story that I said here and biology. Whether or not it's exactly this equation, fine, there's all sorts of interesting variations on it. But something of that form is definitely happening inside the mammalian basal ganglia. Cool. And this is part of why we think of like dopamine is something about the prediction of it's not a signal of reward, it's a signal of prediction of the reward, or an error in the prediction of the reward. Cool. All right. That was a lot of stuff. Summary of all of that. We can learn to train networks based on reward only. Fine. If you want to play games, yes, you could also just do this as a supervised learning problem if you have a whole bunch of expert players playing a game. People want more than that. People want an artificial intelligence to be able to learn to play a game on its own. So you can train a network based on reward only, and basically the idea is you want to output actions that'll maximize a future reward. In the cases where the number of states is really small, I can just use a lookup table, but the moment it gets reasonably big, fine, let's use a neural network. Whole bunch of interesting options for how to train that network. I will say of those options, actor-critic has probably become the standard. Although, as pointed out in the AlphaGo, in sort of special scenarios, you might want to just have one thing or another, especially if you're planning on using like this sort of that game tree alpha beta pruning approach. Then really the only thing you need is to have something that'll evaluate a particular state. And yeah, the reason they use that in AlphaGo is, yes, right now, if you really want to squeeze as much performance as you can out of it, then you want to supplement these neural networks with that sort of classic tree search. And with all of these things, of course, you do lots and lots and lots of training. There's some interesting questions about, hey, can you improve how much training? There's lots of work going on about trying to figure, can we reduce the amount of training these things need? Because certainly AlphaGo and a lot of its sort of things at that level end up playing more games than a human being would ever play in their lifetime. And so there's clearly something else that humans are also doing. All right, that's your introduction to reinforcement learning. Thank you very much. And I think the next lecture will be going on to deep learning and sort of scaling up to modern AI. And how does all the stuff that we've been talking about in the course so far connect to modern AI? See you then.